Do you do office hours over spring break too? Or no?
No, I don't.
Oh,
So next time I do office hours will be after.
oh, okay.
Yeah, I'll be going out of town spring break this way.
Oh, what are you doing?
Just visiting a friend. We have a friend that lives up in Fresno, so
Oh, that's fun.
yeah, they just had a baby, so we're gonna go visit them.
That's exciting. Yeah, my other friend is going to like a bachelorette party.
Oh yeah,
Like,
nice.
dang, everyone's doing exciting stuff. I'm just like, well, I'm still going home to visit family.
That's good.
I'm not doing anything like riveting.
That's fine. I feel like a week is like kind of too short to do anything like
Yeah.
so crazy.
And I'm not even using the full week because I'm working the second half.
Mm,
Like I'm coming back to Fullerton, going to work and stuff.
gotcha.
It is what it is.
Yeah, that's what summer's for. I feel like summer is a better time to,
Yeah.
have a ton of fun.
I got work during summer too. Got payroll.
It's true.
Well, thank you.
Yeah, of course. Have a good spring break, Sarah.
You too. Say hi to Katie and a friend.
Will do.
See you in a week and a half.
Yeah. All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. Great, great crowd today. All right, how you guys doing this afternoon? Good, good. Okay, so of course today is our last day before spring break. I mean, usually it's like this right before spring break, so not too surprising. But today we're going to be finishing up our lecture notes on impedance. So we'll be going over. I have one kind of example for you guys, but we're going to finish up this unit, and the timing's good because we'll finish up this unit, and when we come back from spring break, we'll be able to start something new. And finishing up the lecture today, this is everything that you need to do for the most recent homework as well. So, things are wrapping up, quite nicely. Okay. All right. So some announcements. Remember, there are a couple tasks for you guys to do that are out there right now. So remember, your midterm project is due the Friday we come back from spring break. So, that's not next Friday, but the Friday after that. So you have about 2 weeks to finish up your midterm project. Homework 3, the next problem set is also due on that date. So we have kind of double duty, 2 things that are due on the same date. Okay. The reason for that is, because the spring break is kind of happening a little bit later this time, and so there's quite a bit of stuff we have to do after the spring break. So we have a midterm exam, we have a final project to do after the spring break, and so I want to make sure that we have enough time for everything. Okay. All right, so any questions I can answer before we get started for today? All right. Okay. So last time we left off, we were talking about this idea of impedance, right? So actually, let me kind of summarize that down here first. Okay. So the idea of impedance is kind of to generalize this idea that, it takes work, it takes energy to pump blood through your cardiovascular system. Okay? Okay. Just like it takes energy to pump water through your pipes or through your faucets, things like that, right? It's not a free process. And the reason it takes energy is that, usually when it takes energy to accomplish a task in reality, it's the laws of physics usually state that there's some kind of force or something that's resisting you from completing that task, right? Because if there's nothing resisting you completing a task, then it would take no energy to do it, right? So in kind of solid mechanics, there are things like physics. These are things not physics. These are things like friction, right? Things like inertia, right? Things that cost energy to overcome because they kind of prevent you from generating motion, right? So the cardiovascular system is the same way. Fluid mechanics is the same way. So there are forces that are always going to be there to impede motion. Okay. And in the cardiovascular system, there are mainly there are kind of a few factors that kind of dominate this resistance to flow, right? So there's viscous resistance, there is inertia. Okay. So those are the usual culprits for a fluid mechanics system. But something that's unique to the cardiovascular system is this thing called the wave propagation phenomenon. Okay. It's this idea that, because as the heart beats, right, that creates pressure waves that propagate along the vessel walls of your system. Okay. Those vessel walls go down and they reflect back. And those, that reflection, causes some impedance to the cardiovascular flow. Okay. So all of these things provide impedance to blood flow. Okay. And so what we're doing in this section is kind of quantifying it, right? Or at least doing the best that we can through mathematical equations. Okay. So this section is it's kind of similar to the 1D equations in that, we're doing all these kind of mathematical derivations. We're doing all this kind of hard work and working through kind of the algebra and the calculus, and we end up with something that is not really that satisfying because it's not an equation that we can really solve by hand, at least in a practical way. Okay. And so, I want to start every lecture with this just to kind of remind you of the big picture. Of kind of the purpose of kind of why we're doing a lot of these mathematics. Okay. And so, for the example that we're going to do today, this is essentially what we're characterizing here, just what this impedance is. And then for the homework, for the homework, I gave you a simpler problem. The homework, I want you to do basically the exact same thing, but just for the viscous resistance, which is something that you can do by hand. Okay. Okay. So with that, now that we've kind of reminded ourselves kind of why we're doing this thing, let's jump back to the example that we were doing last time. Okay. So the example that we were doing last time was that we're looking at a singular vessel, right? So we have a vessel with one inlet and one outlet. It's straight, okay? Pretty much just a straight tube, okay? And we want to take our wave equation solution for the pressure and the flow, and we want to solve for their exact values, okay? And what we were doing was we were kind of in the middle of applying boundary conditions to our solution, right? And so what we said was that the flow rate at the inflow is prescribed, right? So the flow rate at z is equal to 0 is equal to q naught. Okay, so this is something that is known. Okay. And at the outflow of the system, we're going to define something as the terminal impedance, which is the ratio of the outlet pressure and the outlet flow. Okay. And so we're going to assume that this terminal impedance is also known as well. And we're going to give it a symbol z underscore t. Okay. All right. So the next steps in this process is to actually apply these boundary conditions mathematically so that we get our solution. Okay. Because what we spent the majority of time doing last time was we found these kind of general solutions, but they're relative to our constants C1 and C2. Okay. So we want to find the value of C1 and C2 by applying our boundary conditions. Okay, so let's go ahead and do that. Let's try applying. Okay, so let's go ahead and apply our boundary conditions to the general solution. Okay. Okay. And so let me kind of remind you what our general solutions look like. So we have Q of Z and T. Okay. This is equal to C1 e to the minus e to the positive lambda t, or to e to the minus lambda t, plus C2 e to the positive lambda t. Okay. E to the I omega t. That was the time component. Okay. And then the pressure solution, P of Z and T, is equal to minus rho C naught squared times lambda divided by I omega A naught times minus C1 e to the minus lambda t plus C2 e to the lambda t. Okay. So last class on Thursday, I kind of gave you a crash course in PDEs, and we found the solution to the wave equation. Okay. So these two solutions here are kind of the general solutions to just a wave equation. Okay. In case you pursue more kind of advanced math after this, that's essentially that's essentially what these are. Okay. Oh, I'm sorry. So these inside the C1, C2, these exponents should be with respect to Z, not T. I apologize. Yeah, so these terms here, let me highlight it here. These ones should be Z, not T. Apologies. So that's very important. Okay. Okay, so let's go ahead and apply our boundary conditions now. So our first boundary condition is that Q at Z is equal to 0 and T is equal to 0 is equal to Q naught. Okay. Okay. And so for this, we're going to plug it into our flow rate equation. So we don't need to bring P into this at all. And so we're going to plug in 0 everywhere that we see Z. Okay? So we have C1 e to the minus lambda times 0 plus C2 e to the lambda times 0 times e to the I omega times 0. Okay? All right, we make use of the fact that e to the 0 is just 1. And so we're going to just cancel all these out. Okay. And so for our first boundary condition, we get a very simple equation where Q naught is equal to C1 plus C2. Okay. Sounds good. All right, so now let's go ahead and apply our other boundary condition. So our other boundary condition is our known terminal impedance. Okay. So this boundary condition is that ZT, which is our known terminal impedance, okay, this is equal to the ratio of the pressure at the outlet. So P at Z is equal to L and T is equal to 0 divided by Q at Z is equal to L and T is equal to 0. Okay. All right, so then to compute this, we of course need to evaluate our pressure and flow solutions at Z is equal to L, okay? The lucky thing is that, these apply at T is equal to 0, so, we can cancel out that exponential there. Okay. So let me go ahead and do that. So Q at Z is equal to L and T is equal to 0 is equal to C1 E to the minus lambda times L plus C2 E to the lambda times L. Okay, we do the same thing for the pressure and we get something very similar. So we get minus rho C naught squared lambda. All these things out in front is just a constant, so they just kind of travel along with our, they just kind of travel along with our solution. Okay. Times minus C1 e to the minus lambda times L plus C2 e to the lambda times L. All right. And so now what we're going to do is that we're going to take the ratio of these two things. So we're going to divide these two quantities and then set that equal to ZT. And so that's going to give us our second equation for C1 and C2. All right. Any questions on this so far? Just everything that we've done? Okay. All right, so the next step that we're going to do here is we're going to simplify that terminal impedance equation there just to give us something that's a little bit more tenable, okay? So first thing I'm going to do is I see that this factor out in front here that I've highlighted in blue, all of that is just a constant, right? That's not anything that we have to worry about. So to kind of save us some trouble from writing it all down, let's substitute in. Okay. So let's define a new variable called Z naught. Okay. And this is equal to rho times C naught squared times lambda, all divided by I omega A naught. Okay. This is mostly just to save us some writing, but it does kind of help us conceptually a little bit too. Okay. So this new quantity that I just defined here, this Z naught, is known as the characteristic impedance of this vessel. Okay. And so if we do that, right, so we make that substitution and we plug in for that, what we get is Z sub T, the terminal impedance is equal to Z naught, the characteristic impedance multiplied by quantity minus C1 e to the minus lambda L plus C2 e to the lambda L, all divided by C1 e to the minus lambda L plus C2 e to the lambda L. Okay. Now we have this expression here. So it's still a little bit of a mess, but it's at least getting to something that's a little bit nicer. Okay. All right. So I'm going to simplify this. Okay. Let's simplify this in this way. So let's group together the exponential terms. Or I should say, let's group together the like terms of C1 and C2. Okay. So to do that, I'm going to multiply both sides by the denominator. Okay. And so that'll give us, terms without a fraction. And then all the C1 terms I'm going to group together, and then all the C2 terms I'm going to group together. Okay. And so what that leaves us with is Z naught minus ZT multiplied by C1 e to the minus lambda L minus Z naught plus ZT C2 e to the positive lambda L. And all this is equal to 0. All right. So from here, I'm going to make one more substitution. I know it's this derivation is a mess. I think this is probably the messiest derivation that we have in this class. We're kind of just making up new variables and kind of plugging them in, but there's a lot of algebra here. Okay. But part of the reason I do this is to kind of make things a little bit you'll see in a bit, right? Because it kind of helps to illustrate some of the important concepts, which it's there. It's there in the mathematics, but I think without these substitutions, it gets kind of lost in the details. Okay. So let's define a new variable. Okay. And so we'll call this variable capital gamma. Okay. And this is going to be equal to Z naught minus ZT divided by Z naught plus ZT. Okay. And just like our other defined variables, this one has a name, but the name for this one is actually quite interesting. So this is called our reflection coefficient. Okay. So this reflection coefficient, the way that we've defined it, is going to be a number between 0 and 1. Okay. All right. And what the reflection coefficient represents is the fact that, as these pressure waves kind of propagate through our vessel, it's those waves are going to reflect back, right? And that was kind of the whole kind of premise of us kind of going through this whole thing, right? So we know that we have pressure wave propagation in the cardiovascular system. We were able to derive an equation, the wave equation, that kind of shows this from our 1D equations. And then what we have here is a solution to that wave equation, right? The thing about waves in applied math and in physics is that they like to reflect on things, right? And so you send a wave out, it reflects back, right? An electromagnetic wave, light is kind of a classic example of an electromagnetic wave. It reflects off, mirrors and reflective surfaces and comes back. Okay. Basically, any physical phenomenon that whose behavior follows the wave equation has the ability to reflect. Okay. And so, of course, pressure waves that are in the cardiovascular system, because they do follow that same equation, are no exception. Okay. So by defining this variable here, we can kind of define or at least characterize how much reflection, how much of the wave gets reflected back. And there are kind of really two extremes here. Okay. And so on the one hand, if we have a reflection coefficient of 0, right, that's the smallest the reflection coefficient can be. Okay. A reflection coefficient of 0 basically means that there's no reflection at all. Okay. So as the pressure wave kind of passes through this vessel, there's nothing that reflects back. It just kind of passes right through. Okay. Whereas a reflection coefficient of 1, a reflection coefficient of 1 is basically total and complete reflection. Okay. Before I move on with the solution here, I do want to talk kind of conceptually or physically kind of what causes this reflection, because this equation right here, even though it's quite simple, I think kind of illustrates a lot of what that means. Okay, so we're going to take kind of a quick break and kind of talk about the physics of what's happening, at least kind of qualitatively, conceptually, and then we'll finish up with the mathematics after that. Okay. All right, but before I do that, are there just any questions on anything we've talked about so far? Okay. All right, so let's talk about what this equation represents. And so, of course, to understand what this equation represents, we have to understand all the variables inside the equation as well. Okay. So let's give a little bit more definition about the Z naught and the ZT, because I've mentioned them, we've been using them, but we haven't really defined what they actually physically represent. Okay. Okay. So ZT, remember ZT is called our terminal impedance. Okay. Right now, we're essentially using it as just a boundary condition for our system. Okay. But the terminal impedance, what it represents is the total impedance or the total resistance to flow of everything beyond the outlet of this vessel. Okay. Because the cardiovascular system, it's not just a bunch of isolated tubes, right? And so we have our one blood vessel of interest here, but in reality, the blood continues from, right? So it continues to a bunch of other different vessels in the cardiovascular system, right? And so it's going to continue out and branch out, right? To all different kinds of blood vessels. So of course, all those vessels that occur downstream of this tube, those are going to provide their own impedance or their own resistance. Okay. So the terminal impedance, what it does is it represents the resistance of all of these vessels down here that we may not necessarily see in our current, in our current domain. Okay. So that's what the terminal impedance represents. It represents kind of the impedance of kind of the combined effect of everything downstream. Okay. Okay. So let's look at Z naught. So Z naught, we've defined that as the characteristic impedance. Okay. So that's a new thing. We just introduced it today, but I just kind of say, let's see characteristic impedance, and then we kind of moved on, right? Let's actually define what it represents. So the characteristic impedance, if you look at its expression, right? So if you look at kind of our formula for the characteristic impedance, I think we had it right here, right? Most of the variables in this equation are parameters of the vessel of interest. Okay. So things like A naught. A naught is the reference area for this vessel of interest. C naught is the speed of is the wave propagation speed in this particular vessel, right? Lambda, property of this vessel, right? Omega is a frequency of oscillation in this vessel. And rho, of course, is the density. Okay. So this characteristic impedance, what it is that, as the blood flows through this vessel, it goes from the inlet to the outlet, right? Travels along this path here in pink, right? It's going to experience some impedance to flow, right? It's going to take energy, a finite amount of energy for the heart to pump blood through this one particular vessel. Okay. So the characteristic impedance characterizes that. Okay. So the terminal impedance is all the impedance downstream. So everything that's kind of beyond the current vessel. The characteristic impedance is the impedance of this actual vessel itself. Okay. Okay. So now that we've kind of characterized those things, let me write down the equation for the reflection coefficient one more time. Notice how the key kind of part of this equation is what happens in the numerator. Okay. In the numerator, we take the difference between the characteristic impedance and the terminal impedance. Okay. Okay. And basically, whenever these two are different, so if Z naught is different than ZT, if Z naught is different than ZT, whether Z naught is higher or ZT is higher, right? Then we're going to get some wave reflection. Okay. I guess maybe, I think maybe I kind of misspoke earlier that the reflection coefficient is the absolute values between 0 and 1, but it can also be negative as well. So it actually goes from -1 to 1, depending on what's higher, ZT or Z. Okay. A negative reflection coefficient, all it means is just when the wave reflects, it just turns upside down, right? So it still reflects, it just kind of reverses in polarity. It reverses in sign. The only case when you don't have any reflection is when the characteristic impedance and the terminal impedance are exactly the same. So this point right here, this point, this observation, or kind of this formula here for the wave reflection, I think is one of the really key points of the section where, the locations where you see wave reflection in the cardiovascular system are cases when you go through a change in impedance, right? So when you're either going through a bifurcation or you're going through, a big vascular tree and the impedance is changing as you go through, those are cases when you see wave reflection, right? If you're going through a relatively simple vessel that doesn't change any impedance, then there's not going to be any reflection from it. Okay. Any questions on this? Okay. All right. So that was kind of an aside, right? So a very important aside, but an aside from our derivation nonetheless. So let's get back to our derivation. So with this defined, with the reflection coefficient defined, and as well as our inlet boundary conditions, we can use those to solve for C1 and C2, which are the coefficients in our general solution. Okay. All right, so C1, and of course, I am skipping a bit of steps here just for the sake of time. C1 is equal to Q naught divided by 1 plus lambda e to the 2 lambda L. Okay. And C2 is equal to Q naught gamma, the reflection coefficient, times E minus 2 lambda L divided by 1 plus gamma e to the minus 2 lambda L. All right. So finally, after 1.5 lectures, we finally have the solution to our wave equation. Okay? And that's basically these two parameters here. Before we jump into an example, I do want to define one more term. Okay. This last term that I want to define here is something called the input impedance, which I'll kind of define what that means physically in a second. Okay. And so what the input impedance represents, okay, so let me go ahead and draw our tube again, okay? And in addition to this tube, let's go ahead and draw all the downstream vessels as well. So we've already defined the terminal impedance, which is all the impedance kind of downstream of this vessel. The characteristic impedance is just the impedance of the particular vessel in question, okay? What about this entire system, right? So what about the combined effect of this vessel itself and everything downstream, right? Basically, what we're saying is that if we were standing right here, right? So let's say we were a blood cell, we were standing right at the inlet of this vessel, what is the total amount of impedance that we're going to experience as we flow through this tree? Okay. So of course, this is going to be the combined effect of both the characteristic impedance as well as the terminal impedance. Okay. And so we define this quantity as the input impedance. Okay. And that's usually our holy grail in this case, right? So, if we were to kind of start at the beginning of a vascular tree, how much total impedance will we see from this vessel and everything beyond that? That's our input impedance. Okay. And so mathematically, the way that we define this is that we take the ratio of the pressure and the flow at z is equal to 0. So Zi, which is the input impedance, is equal to pressure at z is equal to 0 and time divided by flow rate at z is equal to 0 and time. Okay. Which we can find mathematically, right? And so our formula for the input impedance Zi is equal to Z naught, the characteristic impedance, plus 1 minus gamma e to the minus 2 lambda L divided by 1 plus gamma e to the minus 2 lambda L. Okay. So usually when you're given kind of these impedance problems or total resistance problems, this is what you're looking for, right? So a problem like this will give you kind of an entire vascular tree, a complicated kind of system, and you want to find out what the input impedance is for that tree, or maybe the total resistance of that entire tree. Okay. All right. Any questions on this before we do an example? Okay. All right. So let's do an example. Okay. So let's find the input impedance of a simple bifurcation. And so a bifurcation, we have one vessel coming in. It's going to split into two vessels like this. Okay. So we'll call this vessel 1, call this one vessel 2, and vessel 3. Okay. Let's assume that the characteristic impedance of each of these vessels is known. So we have Z naught 1, Z naught 2, Z naught 3. Okay. And we also know the terminal impedance of both of these as well. So we'll call this terminal impedance 1, terminal impedance 2. Okay. All right. And so what we want to find is we want to find the input impedance to this, right? So we know that blood is going to flow from left to right. So we're going to solve for the input impedance to the tree, which is this quantity right here. Okay. Okay. So let's go ahead and do that. Okay. All right. So to actually solve for this, we're going to need to bring in a little bit of knowledge from circuits. Okay. Because from this perspective right here, we have a vessel that kind of branches off. What we can say is that vessels 2 and 3 These ones are parallel to each other. Okay. Okay. You guys remember how to add parallel resistances? And so if you have two resistors in parallel like this, you have R1, R2, okay? And we want to find the total resistance or the equivalent resistance to all this, okay? Right, where R total right here is kind of just one resistor that represents both of these combined resistances. Okay. Then our formula for that, if R1, R2 in parallel is 1 over R1 plus 1 over R2 is equal to 1 over R. So this is the formula right here for combining resistances in parallel. Okay. All right. So for impedances, we're going to do the same thing. Okay. Because right now, as it stands, in this tree right here, okay, we don't have enough information to compute the input impedance of vessel 1, right? That's what we want to find, right? But we do have all the information that we need to compute the input impedance of vessel 2, as well as the input impedance of vessel 3, because we're given their terminal impedances as well as their characteristic impedance. Okay. So that's all the information you need to compute the input impedance of a vessel. You just need to know its terminal impedance as well as its characteristic impedance. Okay, and we're given both for vessel 1 or vessels 2 and 3. Okay, vessel 1, we're given the terminal. We're given the characteristic impedance of vessel 1, but we don't know what its terminal impedance is because its terminal impedance can depend on whatever 2 and 3 is. Okay. Okay. So let's go ahead and plug in for those. Okay. And of course, I'm kind of simplifying the steps here, but you would have to kind of plug into all the formulas, right? And so, first thing that you would do for each vessel, so this for vessel 2 and vessel 3, okay? You would first compute its reflection coefficient. So we'd have gamma 2 is equal to Z naught 2 minus ZT. I kind of messed up the numbering here. Actually, oh, that's fine. So for vessel 2, the terminal impedance of vessel 2 is ZT1, right? So we have ZO2 minus ZT1 divided by ZO2 plus ZT1, okay? And then the reflection coefficient for vessel 3 will be ZO3 minus ZT2 divided by ZO3 plus ZT2, okay? And so with this information, we can compute their input impedance. So ZI2 is equal to ZO2 times 1 minus gamma E to the minus 2 lambda L2 divided by 1 plus gamma E to 2 minus 2 gamma L2. Same thing for vessel 3. So ZI3 is equal to ZO3 times 1 minus gamma e to the minus 2 lambda L3 divided by 1 plus lambda e to the minus 2 lambda L3. Okay. We're essentially just plugging into the formulas that we know. It's just there's a lot to plug in because there's a lot of variables to do. And presumably the gammas for each of these, or the lambdas for each of these two vessels are different as well. Okay, so you gotta make sure you do that. It gets even more complicated because these also involve kind of complex numbers. So this is kind of another thing that is typically done in math, not as much kind of done by hand. Okay. So, after going through that entire kind of song and dance there, we're able to get the input impedances of vessels 2 and 3. Okay. So since these two vessels are in parallel, okay, they're basically on two parallel paths that kind of have the same origin, right? So they both come from vessel 1. Let's combine these impedances in parallel. Okay. Their combination, right? Because the inlet, bless you, because the inlet of vessels 2 and 3 is the same as the outlet of vessel 1, right? This combination will become the terminal impedance of vessel 1. Let me go ahead and draw it out again. Okay, so this is vessel 2, vessel 3. Okay, ZI2. I'm drawing it kind of slightly off the junction, but right as we split off the junction, we get the input impedance of vessel 2. Okay, so this would be ZI2. And then in green right here, this would be ZI3. Okay. That's the impedance that you experience kind of right at the mouth, or right at the inlet of those two vessels. Okay. So what we're going to do now is we're going to combine both of these in parallel. Because if you look at this location right here, and I'll draw a third dot just so you can see, right? This location right here is the terminal impedance of vessel 1. So this is the terminal. And so to get that terminal impedance of the parent vessel, we just have to combine ZI2 and ZI3 in parallel. Okay. Okay. So if we do that, we have 1 over ZE1 is equal to 1 over ZI2 plus 1 over ZI3. Okay. And so we combine these together, we get ZT1 is equal to ZI2 multiplied by ZI3, all divided by ZI2 plus ZI3. Okay. Okay. So now that we have the terminal impedance of the parent vessel, we can go through the same process that we did for vessels 2 and 3 to get its input impedance. Okay. All right, so first thing we would do is we would compute the reflection coefficient, Z1 is equal to characteristic impedance of vessel 1 minus terminal impedance that we just computed, all divided by their sum. And then the input impedance, ZI1. Our final goal is Z naught 1 multiplied by 1 minus gamma 1 e the minus 2 lambda L1 divided by 1 plus gamma 1 e to the minus 2 lambda L. All right. And so unfortunately, because we don't have a very good calculator for complex numbers in our head, we can't do imaginary numbers. This is as far as we can take it, right? And so if you actually wanted numerical values, you would have to kind of plug it into MATLAB. Okay. So what I wanted to kind of highlight from this problem is not really the formulas itself, or not really the result. It's kind of the procedure that we took to get here. Okay. And it's that procedure that you're going to apply in the homework problem. All right, so we'll discuss the homework problem in a bit, but are there any questions I can answer before we get to that? Okay. Okay, so that basically concludes this this section here. But before I let you guys go today, I did want to mention something about the homework. Because the homework is a little bit different. It's basically a simplified version of kind of what we just did. So on the homework, what I'm asking you to do is to compute basically the total viscous resistance of a vascular tree. Okay. So same idea, but instead of doing total impedance, we're focusing just on viscous resistance. Okay. And the reason for that is because we have a formula for viscous resistance, and it's an algebraic equation, which is really nice. Okay. So this kind of goes back. We've seen this formula a couple of times. We've seen this in our lump parameter modeling section. We also saw it in our kind of review of fluid mechanics way back when, right? So this formula is 8 mu times L divided by pi r to the fourth. Okay. So this formula right here characterizes, the resistance of, just from viscosity of fluid flowing through a pipe in a steady state format. Okay. Okay. And so this single vessel is, of course, going to have a fixed value of the length as well as a fixed value of the resistance. Okay. Or fixed value, fixed length and radius. Sorry. Again, my R is mixed up. Okay. So let's say that you're given a vascular tree, right? So let's say that we're given a vessel, that maybe looks like this. Okay. We have a complex network of vessels, okay? Not too dissimilar to what you would see in the cardiovascular system, right? So what you're going to be asked to do on the homework is, based on the formula that we have above, and based on the branching pattern of this vessel here, compute the total resistance of this entire vascular tree, okay? So total resistance is basically kind of the same idea of input impedance, right? If you were to start as a blood vessel right at the entrance of this entire tree, right? What's the total amount of resistance that you'll feel as you experience as you flow through the tree? Okay. Okay. All right, so we're not going to compute it here just because it requires a lot of numbers, but I will kind of give you the game plan. I'll give you kind of the recipe for this. Okay. All right, so what will be given to you in these types of problems is I will give you the physical dimensions of every vessel in this tree. Okay. So basically every single vessel will be labeled with a number. Okay. I'm just going to put some numbers here just as an example. Okay. So this right here just happens to be a 13 vessel tree. Okay. So all vessels 1 through 13, you'll be given their length and you'll be given the radius. Okay. You'll be given the viscosity of blood as well. Okay. And you'll be given a picture kind of the branching pattern of this vessel. So basically what I have to you there. Okay, so to solve these problems, you're gonna follow you're gonna take the following steps. Okay. All right, step one. So step one is to take the physical dimensions of each vessel as well as the viscosity that's given to you and compute the individual resistances of every single vessel in the tree. Okay. Okay. So that's not all that different from our last example. So our last example, we were working with impedance, okay? And so in that case, for every vessel that we could, we computed the input resistance or input impedance, excuse me, okay? We took the terminal impedance, we took the characteristic impedance, and we computed the individual input impedances, okay? This one's a little bit different, so you can actually do it for every vessel in the tree. You don't need to you need to wait, okay? So every vessel in the tree, R1 through 13 should have a resistance after step one. Okay. Number two. Number two, you're going to start from the back of the tree. So start with the vessels that are nearest the output. Okay. So if you look at this diagram here, I'm looking at all the terminal vessels here. So vessels 8 and 9, vessel 12 and 13. I would probably start with those ones, okay? Because they're right at the very ends of the tree. Okay. So starting at the back of the tree, start to combine resistances in series or in parallel, depending on the geometry. Okay. So if you have two vessels in parallel, just like we did in the last example, you're going to combine their resistances in parallel. Okay. So for example, we can replace vessels 8 and 9 here with a single resistance. Okay. And so we can combine it together into a single vessel. We'll call this vessel 8, 9. Okay. And so since vessels 8 and 9 here are in parallel, if we do 1 over R8 plus 1 over R9, is going to be equal to 1 over R8, 9. Okay. And so since you'll have the numerical value for R8, you'll have the numerical value for R9. You can solve for the value of R8, 9. Okay. And you'll do the same with 12 and 13. Okay. So you have 1 over R12 plus 1 over R13 is equal to 1 over R12, 13. Okay. So in those cases, we have kind of two parallel combinations. Okay, number three. Number three is that once you've done this for all the terminal vessels, so all the ones at the very end, combine those in series or in parallel with its nearest neighbor, working your way towards the end. So the idea is to kind of, keep lumping together resistances and keep adding them to your combined total until you encapsulate all the vessels in the tree. Okay. So from 8, 9, its immediate neighbor is vessel 7. Okay. And vessel 7 is in series together with 8 and 9. So when two resistors are in series like that, you just add their values together. Okay. So let me go ahead and draw that down here, right? We have vessel 7, 8, 9. Okay. We already know the combined resistance of these two from the previous step. So the combined resistance is R8, 9. Okay. And so if we want to combine this R8, 9 together with the resistance of vessel 7, okay, so this has a resistance R7 that we found in step 1. Okay. Let's combine these in series. Okay. We'll call this R789 is equal to R7 plus R8. All right, so you're going to keep doing that, okay? And so you're going to do this kind of several times, right? And so it may take, several combinations of series and parallel, depending on how big the tree it is, okay? So you're going to keep doing this. Okay. keep doing this until you reach the inlet, okay? Until you reach, you combine all of the resistances into one gigantic resistance for the entire network. Okay. And then that one resistance, or the value of that one resistance, that's going to be your answer. Okay. All right, so kind of a simplified version of kind of what we do, what we've been doing with impedance. So no imaginary numbers, no complex numbers. There's no, a bajillion variables to keep track of. So it's just simple resistance, but just this idea that, when you have vessels that are branching in parallel and in series like this, you can combine their things together. That's kind of the main upside that I want you to take from this. All right, any questions on this? Okay, all right, so this is the last class we have before spring break, so I'm gonna go ahead and end it a little bit early. So thank you guys for coming today. I know it's it's the last class before spring break, so it's always a bit hard, but so hope you guys have a great spring break. Definitely take your time, rest up, take care of yourself, and I'll see you guys after the break. Okay, all right, so see you guys in a week and a half. Thanks, Sebastian. You too. Have a good one. You too. Have a good one.
Do you mind if I show you the project?
Sure. Yeah.
So this is the picture that you had given me.
Yeah.
To do it on, and this is what I have so far.
Okay.
This vessel, I was struggling to get it to look like this one over here.
I think it's pretty good.
Okay.
It looks like you have it, yeah, it looks like the size of the vessel is just fine.
Okay, and then I did the main thing just because that's how they did it, but
Yeah.
yeah.
I think it's okay. I think you're probably gonna need it for the mesh and stuff. But
Okay,
no, it looks good. Looks really good.
thank you.
Yeah.
Do you have any plans for break?
I'm gonna visit a friend in Fresno, so she's a good friend of mine from college, and she just had a kid recently, so we're visiting her, meet her baby.
Crazy because my brother just had a baby, and it's crazy like how different like the house dynamic is now. Like everyone wants to come over, and I want to go visit all the time too. So.
Yeah. They're only gonna be that small once, and so
Yeah.
you gotta take advantage of it. Thanks, Sandro. You too.